Yeah, well, so hi, I'm Göbels, a PhD candidate of the RWTH in Aachen, and I will present my paper today, Transfer of Implicit Semi-Formal Textual Location Descriptions in Three-Dimensional Model Context. It's a quite long title, I hope it's kind of precise. And so, okay, that is not working. Okay, no. So directly starting, when you want to locate yourself in space and you don't want to use some kind of external reference system, the easiest way to do it is to use like your body-centered orientation. So use like front, rear, right, and left, and with some kind of point of interest or like a landmark, you can like describe the relation to your body or like from some object without using GPS tracking or some coordinate system. You can just, I think like every one of us does it each day using this kind of orientation or like relation descriptions. Okay, I don't see that here. So, and that is also the approach for localization and assigning of information that the German bridge inspection process is using for localization of information. So now that's jumping into the topic. So when you want to inspect a bridge, of course, you should know in which bridge you currently are. And then you have to document the viewing direction. So you have to see like, I'm looking into the city, into the direction of city B, and then based on that, you can make statements like, that's the rear abutment, that's the rear, the left railing, and so on. Sorry, I don't see my slides here, it's confusing. And of course, you're there to inspect the damages, of course, and then you can also use the same approach, saying the front abutment is damaged at the lower right area, or like there's damage at the end of the bridge deck. And that everything without using any kind of external reference system, because you know where you are, and that's the kind of approach they use. And then going back to your office, and then you have to enter everything into a documentation database, and in Germany it's called the Bauwerke, and that's a proprietary closed database system that stores all these textual location information of the inspection, but there's no geometrical representation, no visualization. It just stores this text, and based on that, you enter some impact factor for each damage, and then it calculates a very basic bridge condition grade. And of course, yeah, it's a relational database, so this is how it looks in a simplified view. So we have different tables covering different topics. And of course, there's some data structure behind it, so you're not free to use any words you like. In Germany, it's the ASB-ING, so that's a data model of this inspection data software. And it defines the kind of tables, so the topics which we use to document all these bridge data, so damages, material, but also inspections and administrative data. And for each table, we have also predefined attributes, so like the column tops, and even the contents inside each cell have like a predefined term. So you're not free to use any words you like. You have to choose them from a list of predefined terms to say, so for example, which kind of damage type it is, or the location term in this example. And then going back to the bridge 3 years later, because that's the usual bridge inspection interval, you have first, of course, export all your damages from this software to PDF, print it, and then go on site. Of course, first of all, you have to know like the viewing direction again to interpret all these correctly. And then you might be lucky and find these damages again based on these textual location descriptions. Yeah, so that was a very brief, simplified summary of the German bridge inspection process. And as you can saw, it's a very human expert-based process. So we have to have these experts in bridge inspections that have to go there and make all this work, so have to have the knowledge about the damage, but also have to find the damage first and read all these texts. So it's a very time and cost intensive process. And also with this ambiguous location descriptions, it's sometimes very hard to find the damage, so sometimes they don't find it and they just delete it from the database. And because of this viewing direction dependency, it's also confusing because you always have to look and to think in this direction, but of course your body is moving around, so it's kind of confusing, and I think all of us know this right and left confusion sometimes, so it's a very error-prone approach, and which is, I think it's obvious, it's not machine readable or machine interpretable. And this is the process used for around 56,000 bridges in Germany, because that's all bridges inside this database system. And 45% of them were built before 1980, and that's why 25,000 bridges will need increased maintenance in the next few years, or already needs them, so that we have more often inspections or demanding measures. So yeah, this kind of approach with this immense workload will not work out, probably. And that's why currently, and as I think all of you know, that digital twin approaches for bridge maintenance are being explored in several research projects and also in some practical use case studies. And also this research was part of the TwinGAN project, where we aim to develop automated methods to generate digital twins of existing bridges. And having the advantages of the digital twin, that we have a model-based information and of course computer-supported analysis, and leading to a predictive maintenance approach in comparison to the reactive maintenance approach we have right now. And we did not do that alone, so another department, so the GIA department, also from the Aachen University, was in charge of creating the point cloud and segmenting it. And the TU Munich was then deriving a 3D model out of it, using different approaches. I won't go into details about that. For me, it was important we have now a 3D model from our bridge. And also the Ruhr-Universität Bochum was part of that project, and they created methods to detect damages in point clouds and pictures. And our part was how to integrate now all these existing data from this inspection database, but also from all the construction and installation information, how to integrate that into our digital twin, because we need to know about the past to predict the future. So that was one main task, and linked to that, or connected to that, we also had to think about how to interlink at all these different resources together for our digital twin approach. So we have lots of heterogeneous resources having different data types, provenance, and quality, and we decided to use a linked data approach for that, so that we can interlink all these resources on object level, so that we have really precise links between the different resources. And there are already ontologies to represent, for example, the IFC model using IFC-OL, or also the bot ontology. We used the ontologies of the information container for linked document delivery to represent all the files, like the construction plans, pictures, but also the point cloud in our approach in RDF, so in the linked data format. And there are also ontologies for representing the damage information, so the DOT and the AOI ontology. And we did also, in a previous task, create or converted the ASB-ING data model, which is the data model of this inspection data, into an ontology, which then allows us also to convert all these databases into RDF graphs, so that from this proprietary closed system, we have no open and accessible RDF graphs, which we can then further link and process in this process. And of course, now the work I will present today is that we used linked data as a tool, so it's what enables to interlink these, but of course the links between the data sources are not happen magically, and that's why what we aimed here, so that we transfer this textual assignment and localization of information, which is natural to humans, to the 3D model. So to identify first the meant or affected component by a bridge, by a damage, and then based on that, define and create a damage area representation, so that we have a first time a spatial representation of this just textual information. And as a result, we have then links between the old and the new data sets, so that the geometry model is enriched with all the semantics, and the semantics have now the first time a geometrical representation. So now coming to the previous work, just very quick. So I said that we converted the database tables into RDF, and we used our ontology for that. And then this is how one damage object looks in RDF now. So basically the columns are now the properties. And when you look at it, this kind of damage object actually have lots of different information inside. So we have data that's concerning about the damage type, and some more, I excluded them here, but also the component information. So we know which component type is affected and the location of it, but we don't have any ID or something. And we know about the damage location, but they only having you the same property location description. So, and because that was kind of confusing for further processing, we decided to split that object up into smaller ones that have a more precise semantic meaning. And that's what we came up with. So we store all information that is describing the component and its location in a component definition object, and the information that is really defining the damaged area in an area of interest object of the AOI ontology from Hamdan and Scherer. And because we have now everything in RDF, we were able to use Sparkle queries, and we were then able to link our component definition object to the real component, which is also inside the Bauwerke data, but it was like in some completely different table, not linked at all. So now we derived from that by comparing abutment in front to some object which has the class abutment and the location first span, that we know now which component is really meant, and that enables an object-based damage documentation, so that we use the dot or the AOI ontology to know exactly which component is damaged semantically here. And that is now our basis for the process I will explain now. So this transfer of the textual location to the 3D model is basically divided into 3 parts: data preparation, localization, and linking. And the preparation is that we have to analyze first all these terms we are allowed to use to describe a location, because they are like predefined from this national data model, and we had to first categorize them. And based on that, we are also had to prepare the IFC model we got in the Twingen project for this process. I will explain this in a minute. And based on that, we were then able to first identify the component by its type and the location information. And then if we found the component, we used the damaged area location information to kind of split these up and intersect them, so that we then at the end have some damaged area representation. And finally, we're linking that together so that we have links between the IDF graphs from the inspection data and the 3D model. And we just do this for each component until everything is processed, and we have lots of links between these data sources. So coming to the data preparation, so these are the location terms, some of them that you are allowed to use when locating a damage. And there are 206 of them predefined, and 60% of them are viewing direction dependent. And you are allowed to use a variety of terms to kind of express the same location, which is some German thing, I think. We can use lots of words to say the same. And we can use 2 ways of context referencing. And these context referencing ways are like once referring to the whole bridge structure. So at the end or at the beginning of the bridge structure, you always have to have in mind the whole bridge. And for the other ones, like component-related terms like top, side, middle, bottom, so they are just describing a logical subpart of any element, so we don't have to know the whole structure for that. So that's the 2 categories. And first we want to transfer these bridge structure-related terms to our 3D model now. And for that we have to first align the the bridge model to our process. And we say that it's mandatory that the origin of the model coordinate system is at the center of the bridge, and that the x-axis is kind of the main axis of the bridge. And based on that, we can say now that all negative x values refer to front and all positives to rear. And because we're looking from front to rear, that is then defining the viewing direction. And then finally, we have to align or like rotate the model until it fits to the outside recorded direction, like from city A to B. And we did this in this approach just manually inside the modeling software. So I know there are automatic approaches for that, but from this stage, we just did this manually. And further, you can also say now that all positive y values are now referring to left and the negatives to right. And the z-axis, the vertical axis is just going up. And now we want to bring that terms to our 3D model. And we also have to have some mapping because we use an IFC bridge model. And we now need a mapping between this RSB-ing component types and the IFC classes. And based on that, we are then able to create zones on top of our bridge model that represent these kind of location terms. And also defined by this data model, we know that the end and the beginning of the bridge structure is defined by the road junctions, and we just filter then the bridge model for it, and then define like an offset to each side of them, and then create a bounding box representation. And we did the same for the first and second span here in this example, because they are defined by the substructure components, and right and left side of the bridge is just a bounding box divided during the main axis. And then we store that just as a IFC proxy elements in another file, just to have a bounding box representation. And we also have to assign these component related terms to the coordinate system. So what we basically did is to assign each of these terms to one category, and we decided to split up each axis into 3 main parts, because it's also coming from the data model that each direction can be split up into like front, middle, and rear, and right, middle, and left. And that's, we just assign now like top side and on the top to the category Z top. And by that, we also kind of limit the variety of expressions we are allowed to use. And at the end, we just have 9 different categories instead of 50 different terms. So now we want to locate our information, like to bring that to the 3D model. And here's like a quite complex example, but you are allowed to say that in the inspection data set. So there's a damage on the rear lower right side of the third beam from the left in the second span. And this is how it then looks in RDF. So we know the component is somewhere in the second span and the third component from the left. We know that it's a longitudinal beam according to the RSB-ing classes, and we know now the damaged area is the bottom, right side, and rear. And now with our mapping, we just filter our model for the IFC beam type. So now we have all IFC beams and intersect them with the bounding box that represented the second span. And all model elements that lie inside these box are now selected. And now we have the second component, the second term, third component from the left. And as we know from before, that positive y values refer to left, we can now order the axis of each component and just then count the third component from the highest value. Now we have our found our component, so it's a real IFC beam component having UID and stuff, so that's what we want. And what we also did is to convert, what we did also before, convert the whole IFC bridge model into RDF using the IFC to LBD converter, because that allows us now to create a link between the inspection data set and the RDF, the bridge model, on object level. So that's now first component is found, and now we want to highlight the damaged area on that. And we don't do that with the component itself because it's too complex geometry. We create a bounding box which closely encases that component. And as I said before, we divide each of these component-related terms into 9 categories. So we have like these 9 different bounding boxes based on the component. And as we know, Now that bottom is the category Z bottom, right side is Y right, and X rear is rear. We can now intersect these bounding boxes, leading to some smaller bounding box, which is already defining the bottom and right side, and then we intersect that with a rear bounding box, and that is then finally leading to our damaged area representation. So it's kind of simple process. And that is finally our damaged area representation box. And we also store that as just in this stage as a proxy element inside another IFC model, convert that also to RDF, and then we can create the link between our inspection data and the IFC model. And the whole process is on GitHub, you can look it up. And we applied, of course, this process to use case example. That's the bridge you already saw before. It's from the TwinGAN project, and it's a multi-span girder bridge from 2002, and its inspection data had around 40 damages with 33 components. And like this, so like this kind of flat bridge, 75% of all bridges in Germany have the same structure, which leads to around 43,000 applicable use cases for that approach. And we used now in this case a hand model, the IFC bridge model from the TwinGAN project, and we were able to achieve a success rate of 72%. So we were able to transfer 72% of all component and damage information, like textual information, to our 3D model. And we used the results to implement a linked data viewer that now accesses all the formerly just database stored textual information via the 3D model now, and we can also highlight the damaged areas and see now directly where damages are and see like the spatial extension and the density. And yeah, in detail, we achieved to transfer 82% of the damages, but just 60% of the components. But that's mainly because all the other components were just not modeled in our very simplified model. And we were able to locate 57% of the damages on a concrete area, and just the rest were just assigned to a whole component because it was modeled like continuous or something. And the rest was also because of not modeled or wrongly modeled elements. So to sum up, we created a process that, based on this textual location, is able to identify model components in an IFC model and locate and create conceptual damaged area representations, which is then leading to an interlinking of the existing and the new data sets, which now enables the first time to have an explicit, independent spatial representation of this just formerly implicit ambiguous textual information, which is also supporting the on-site inspection, because when we have a 3D model, we can easier compare it to our real-world object, and also improve remote inspection, because we can now easily talk with our colleagues about this, having a better base for communication than just text. And what is like the broader view now, and of course it's computer accessible. Now we can do spatial analysis like the density of the damage or most damaged areas. And what is in the broader picture important is that we now create like an approach that automatically interlinks the existing data sets to our newly 3D model. So we have quite a good basis for then further develop some digital twin approach, because we already have like a semantically enriched 3D model, which we can then add sensor data, point clouds, pictures, and so on. Of course, there are some limitations, and all of them are kind of based because I use this model, this bounding box approach. So, of course, the whole process is not that easy with curved bridges, because then the whole complex geometry gets much more computational effort. But still, 33,000 bridges are just very simple straight bridges, so we have still a lot of use cases for that. The damage area representation is always 3D now, but of course I know the most damages are just superficial types. And this 3 division of each axis is also just some division we made, but it's mainly maybe not the meant area of the inspection engineer. And what is most important, of course, is that these bounding boxes kind of mislead to very precise damage representation now, but our input was very vague, right? So this kind of misleads to more accurate representation, but the information for that is not really there. So we want to look into more fuzzy visualization and representation of that information, so that also analyzers don't have the wrong basis. And to conclude, this is a rule-based approach, so it's not like machine learning. We can already work with very small data sets with a success rate of 72%. And for our approach of like linking on object level to specific locations, it was like accuracy achieved enough. And what is also important, it makes like the current data already available. So we really used like the data which is out there in practice and used that for our approach, and we don't have to rely on artificial data sets, and we can just say so we don't have to wait until the government or something is doing a modern databases that can be accessed via an API or have like a more object-oriented structure. We can already use that with our approach. And what is just a side note, so we have a success rate of around 70%, and assuming these 43,000 bridges, and each of that has about 70 textual location descriptions, but even more. This would lead to over 2 million transferred textual location descriptions, which then of course can serve as training data for machine learning approaches in the context of NLP and 3D models, also outside the domain. Of course, we're not limited to bridge inspection and construction, also in cultural heritage and stuff. They are all a lot using this natural language approach of documenting and describing location of information. So, and as a future work, because I know there won't be like 3D models, IFC models for all of the 43,000 bridges. I want to look more into how to come up with a more schematically basic bridge model just based on topological rules, the dimensions we already have, and some like national guidelines. But that's like just a very future work. I didn't look into that. And of course, and then use like just relative coordinates or some vectors to describe the damaged area instead of this very sharp bounding box approach that could then be also easily be included or like viewed in the point cloud or even like in an aligned construction plan. Yeah. So that was anything from me. Thank you for your attention.